Hello, so this is Ian and I'm back with a video. This time I'm going to solve an interesting reaction kinetics question. So let us first take a look at this question over here. It's modified from a school prelim question. So nitrogen dioxide, NO2 is a brown gas. Nitrogen dioxide and carbon monoxide react according to the equation below, producing colorless products. So now we see a method to track the reaction rate, which is to track the color intensity. In this case, it's a clock reaction because we are waiting for the time taken for the brown color to disappear. So this is the prominent visual change, the disappearance of the brown color under different concentration of reactants, and the results were obtained. Temperature was kept constant. Okay, so now we first need to relate this time taken over here. How does it relate to rate? And so can we just use the simple approximation of rate is proportional to 1 over time? So to find out whether we can do this, we have to go back to our funded definitions of reaction rate. So reaction rate is defined as negative d NO2 dt, am I right? And is being approximated by negative final NO2 minus initial concentration of NO2 divided by the time taken. So this is an instantaneous rate. Whereas this is the average rate. So this is an approximation. And we note that the final concentration NO2 is likely to be very close to 0 because the brown color disappears, or it will be a very small constant value. So we can just take this to be 0 and then we'll get initial concentration of NO2 over time. So if the numerator was a constant, then we can just take rate is proportional to 1 over time. Unfortunately, right, we realize that concentration NO2 changes between the experiments. So now we have to use this as an approximation for reaction rate. So I shift this over to this side and we can add a new column to our table, which is the reaction rate. And so we take 0.0120 divided by 92 to get the reaction rate. And according to the calculator, the answer is 1.30 times 10 to the power minus 4 mole per dm cube per second. For experiment 2, doing likewise, you get 5.22 times 10 to the power minus 4 and 1.30 times 10 to the power minus 4. So let us take a look at the reaction rates. So we realize that comparing experiment 1 and experiment 3, right? Concentration of NO2 is kept constant. Concentration of CO, carbon monoxide, doubles and the reaction rate remains the same. So what can we conclude? Reaction is 0 order with respect to carbon monoxide. Then if you were to compare experiment 1 and 2, right, when the concentration of NO2 doubles, the reaction rate, right, quadruples. So we can then conclude reaction is second order with respect to NO2. So then now we are asked to write the rate equation, and the rate equation will simply be rate equals to K times NO2 to the power of 2. Next, we are asked to deduce the time taken for the brown color to disappear under the same temperature conditions, rather, there's a typo here, same temperature conditions, and with concentration of NO2 equals to 0.0060 mole per dm cube and concentration of CO equals to 0.0170 mole per dm cube. Okay, so we know that since rate equals to concentration NO2 over time, so then the time taken equals to the concentration NO2 divided by the rate. And so we know that the new time taken, say over the time taken for experiment 1, would be equals to the new initial concentration, I'll just call it NO2 new, divided by the concentration NO2 in experiment 1 times the rate of experiment 1 divided by the new rate. Right? And then bring this over to the other side and substitute in the values. We get the new time equals to 0.0060, right? Since our new concentration is 0.0060 divided by 0.0120 times what is the initial rate in experiment 1 divided by the new rate. So we are dividing the concentration NO2 by 2, so the rate decreases by 1/4, so it's basically 1 over 1/4, which is 4, and then times the time taken in experiment 1, which we know to be 92 seconds, and this will give us the new timing, which is 184 seconds. So now let us take a look at the next part of the question. Two possible mechanisms have been suggested for this reaction. They are a single-step reaction and a two-stage reaction. Explain why mechanism 1 is not supported by the rate equation. So this question is quite nice. They tell you that mechanism 1 is not supported by the rate equation and ask you to explain why. So how I would answer this would be to say in mechanism 1, one molecule of NO2 collides with one molecule of carbon monoxide in an elementary reaction. Right? Recall, what does an elementary reaction mean? It means that the reaction mechanism is described by a single step. And so this suggests a rate equation of rate equals K concentration NO2 times CO. But the observed experimental rate equation is given by the equation rate equals to K times NO2 to the power of 2. Right? So hence mechanism 1 is not supported. Okay? And then part 4, they tell you that the reaction is exothermic and follows mechanism 2. Draw the energy profile diagram of the reaction. So what do we know about the mechanism? We know that the first step must definitely be the slow step, right? Because we know that the rate is independent of carbon monoxide. So step 2, which involves a molecule of carbon monoxide, cannot be the slow step. So step 1 must be the slow step. So what does this mean when you're drawing the energy profile diagram? It means the first step has the higher activation energy. And we know that what is the intermediate? The intermediate is NO3. So, and we know that the reaction is exothermic, means energy of the products is lower than the energy of the reactants. And we can begin drawing the energy profile diagram already. So, as usual, be energy. And then the x-axis will be reaction coordinate or progress of reaction. It's not time. And the first step is a slow step. I shall draw the intermediate a bit broader so I have space to write the stuff. And I would write now the reactants. So 2NO2 forms NO plus NO3 plus CO, NO3 plus CO form NO2 plus CO2 plus NO. Okay, so we are done, but we need to do some labeling. The question didn't explicitly ask for this, but it's always a good habit to do this. Note that for the labeling of these energy changes, you need to draw single-headed arrows only. And we are done with this question. So yeah, it's not too difficult a question, it's just a pretty interesting question that may trip up some students because they simply take rate is proportional to 1 over time and they'll get the whole question wrong. So as long as you keep in mind the original definition of rate and then determine how rate relates to time taken, then you'll be very safe and this question will be quite easy to you. Okay, I'm done with this. So wait for my next video then, where I'll go through an organic chemistry question.